All right, so earlier we talked about the Young double slit experiment. Now what we're going to talk about is single slit. And so we're talking about diffraction. So basically we're saying you have a laser pointer and you have a single slit. So you shine the light through the single slit and it bends. And this is what you see. So you see a pattern, right? You see the central max, then you have no light, then the secondary max and no light, third, max and no light. Now, by the way, this is really sort of fake. This is really, really tons brighter than this, and this is brighter than that, okay? But they just kind of do it like that so you can see it. So it's called single slit diffraction. Okay, so there's a guy at the time, of Young and all those people back in the day, 1800s, Huygens. So Huygens, he was a proponent of the wave theory of light. So that he has something what's called Huygens principle. So this is the slit, all right? This is the tiny, tiny, super, super narrow slit. And what he said, hey, when we did the double slit and all that, we said that there was like one source of light, right? That would go through two slits. But now we're saying, this is what he said. So here's a wave, right? This is the max of like a plane wave coming in. And he said that, you can divide this tiny little distance into smaller distances, right? And he said, just divide it however many times you want, And he said, each of these points is a source of a spherical wave. Now, he said wavelet because it's a small wave, right? But just, all right. So all I was saying is, you kind of see that, right? So here's the source of this wave. Okay, here's the source of this wave, or something like that, right? So these are all sources of spherical waves, okay? And the wave front, again, just the maxes of the wave, at a later time is tangent to all of these wavelets, all right? Now think about it. If you have like 1 million, of these sources of spherical waves, what are you going to get over here at the screen? You're going to get an interference pattern, right? You have 1 million waves interfering, okay? All right, so wow. In fact, really, how many, there's a huge, there's like an infinite number of these things, right? All right, so, oh gosh, Okay, so, yeah, so this is the double slit, right? Now we're saying we just do a single slit. Okay, all right. Okay, so what we're going to do is we're going to look at 0 degrees. Okay, this is double slit, so we're going to look at 0 degrees and then, non-0 degrees, all right? So here's what it would look like at 0 degrees. So the light, so each wave is just going like this, right? And here, there's no path difference, right? And so you're just going to have constructive interference, so you're going to see this you can see a bright central max, okay? Bright central max, no kidding, all right? So that's for 0 degrees. Now let's do some angle, right? Let's do some angle. So now there are path differences. So we're going to use similar logic that we use for double slit, parallel rays and different path lengths and the whole bit. And this is going to be our result. Now, look, when we did this in the past, we also had the equation for constructive interference. Well, here, again, we're skipping a ton of math, and we're making it relatively reasonable. So here, the easiest equation to get is for destructive interference. A sine theta p equals p lambda. Now here, p is an index. We used to use m. You can use whatever you want to use, right? Here we use p. Who cares, okay? So, p is 0, p1, 2, da, 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 da. All right? So here's your single slit interference pattern. See the super bright central thing, then a dark, then a little bit brighter, then a dark, da, 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 da. All right? So that's the result, right? We're skipping the math. Horrible. Okay, so there you go. All right? Okay, I haven't asked you a question in a long time. Here we go. All right, when light passes through a single slit, dark bands appear on a viewing screen at angles given by A sine theta p equals p lambda. Yeah, we just said that. with P, 1, 2, 3, da, da, da. For the dark bands to exist, what must be the relation between lambda and A? This is totally trig. This is a math question. So pause your video and figure it out. Okay, let's do it. So we have A sine theta equals P lambda. So that means that sine theta is P lambda over A, correct? All right, now, what does sine go between? It goes between 1 and minus 1. You can never have a sine greater than 1. So what does that mean? That means that P lambda has to be less than A, right? Or just say lambda has to be less than A, right? Because sine can never be bigger than 1. So I mean, a pure math question, right? So lambda has to be less than A. Okay, let's forget about the P. Let's say P equals 1, right? Let's say P equals 1. Make it simple. Okay, what happens when lambda equals A? So pause your video and figure it out. Again, this is a math question. When lambda equals A, all right, let's talk about it. When lambda equals A, you have sine theta equals 1. Well, what's theta? Sine of what equals 1? 90. So theta is 90 degrees. So what would you see? So you just see this big white thing, right? Your whole band would be white because theta is 90, right? So you'd only see this big white central bright band. Okay. All right. This is for you to do again. So please figure out Y1 in terms of L, lambda, and A, and use one of the small angle approximations. Because we're just getting Y1. We're not getting Y2 and 3 and all that, you know. Okay, so you work on that, please. All right. Let's see. So just like before, let's see, Y1 is L tan theta 1, correct? But what we have, where'd it go? There it is. But we know that A sine theta 1 equals 1 lambda, right? And so therefore, sine theta 1 equals lambda over A. Small angle approximation, this is L sine theta 1. So sine theta 1 is that, multiply it, we get L lambda over A. Yay! So you should be able to be really good at doing those kinds of calculations, right? So Y1 is L lambda over A. And again, we use small angle because we were right, small angle. We didn't do like P equals 45 or something like that, or P10 or something like that. All right? Now, look at, we just calculated Y1. That's from here to here, right? Okay, so what's the width? Well, just twice, right? Because the width is, this plus that. And they're both Y1, so just double it. So the width is double it, just 2Y1, 2L lambda over A. Well, that's nice. Okay, so what happens to this width when when A gets smaller and smaller and smaller? So just look at the equation. When A gets smaller and smaller and smaller, so this is getting smaller and smaller. So this fraction becomes larger and larger, so the width gets larger, right? The width gets larger. Okay? And, okay, so does that make sense? Well, that means, if this gets smaller, this is going to get bigger, so you're going to have more bending. Well, gee, doesn't that agree with what we said earlier? Earlier we said that the fraction is proportional to lambda over A. Yeah? So that kind of, look at it, it agrees, right? So the lambda, if you have a really large wavelength, what's it going to do? It's going to have a big width. It's going to spread, right? So this formula exactly agrees with what we had earlier. Okay? So that's kind of nice. All right, so yeah, we saw that. Okay, let's say we want to be astronomers, or yeah, let's say or use a microscope. But let's talk about astronomy. It's more fun. Sorry, biologists. Okay. Well, you know, this was a single slit, right? This was the single slit. Well, instead of having a single slit, let's have a circular aperture, you know? So you just have the light coming through a circle, right? So the light's going through the circle, which is a telescope or a microscope or something like that. So I'm not going to go through the derivation, but here's the answer. Okay, here's the answer. So that's what it looks like. So that's what the diffraction pattern looks like when it goes through a circular aperture. And the first minimum, first dark spot, is located at, okay, so here's the equation. Sine theta 1 equals 1.22 lambda over d. D is the diameter of the lens, like in a telescope or a microscope or something like that. Now, if you have small angle, you know, if you have a small angle, then sine theta equals theta, like we learned a long time ago. And so you can just say theta 1 equals 1.22 lambda over d. Okay? Now, this is incredibly important in astronomy. In astronomy, this is called the diffraction limit. Why? Well, think about it. You know, let's say you're looking at a galaxy, or let's say you're looking at two stars. You know, do you want one of the stars to be here and one of the stars to be here or here or here? Better not, because you won't see anything, right? It's diffraction, destructive interference. So basically, you want your images that you care about to be here. And remember, this here is really much dimmer than this. So you want what you're looking at to be inside here. In other words, you want this to hold. You don't want to look at anything outside the central max, right? So you want that to hold, okay? So here's kind of like here's sort of an explanation. I hope it makes sense to you. All right. So let's say you have two stars, and you want to be able to see two stars, you know? Think of it like this. Let's say you're out in the middle of nowhere in the middle of the night, and there's a car really far away approaching you. What do you see? You see one light, right? And then as the car gets closer and closer, you see, oh, there's actually two lights, right? Two headlights. Well, it's kind of the same thing with stars, or, you know? So here, if the two sources are sufficiently far apart, they can be seen as two separate diffraction spots, right? And that's what you want to be able to know. I mean, see, you want to be able to see if it's two stars or one star, or two galaxies or one galaxy, whatever, you know? If the sources are too close together, the diffraction spots will overlap so much that they appear as a single spot. I mean, what is that, you know? A single spot, right? Now here's the thing. Two sources, stars or galaxies or whatever, will be resolved as two distinct sources of light if their angular separation is greater than theta 1. Okay? So that's it, all right? So what do you want? Oh, come on. All right, so there it is, okay? So that's what it is. Now, so in other words, you know, you want to have your telescope so theta 1 is as small as possible, because in order to resolve it, you need something to be greater than that, right? So let's just give you some examples. So what does this really depend on? Well, it depends on the wavelength of light. You're kind of stuck there, right? So if you want this to be super small, what are you going to do? You're going to spend money to make a really large diameter lens, or whatever, mirror or something like that, okay? That's, all right, so here. So here's a 5-inch diameter lens, and you can see a dime at 3.7 kilometers, all right? Well, that's no good. Here, supergiant Betelgeuse, 2.3 meter lens. Look at how far away it is. So it takes light 430 years to reach us. All right, but you could see it. Okay. This is the Big Island, Mauna Kea. These are the two Keck telescopes. 10-meter mirrors. They can resolve something 0.01 arc seconds. What's an arc second? Well, you look at a degree, and then you split that up, and you have like arc minutes and arc seconds. So incredible resolution. And so that the next phase of telescope building, they want to get a 30-meter diameter mirror, and then you get to see further away. It's awesome. Okay. So let's see, where are we? Okay, please figure out the width using this equation and everything that's here. Please figure out, it's kind of like what you did before, figure out this width. All right, so for a circular aperture, use everything you've done, use those equations, and figure out the width. So pause your video and do it, please. All right, let's do it. So in my opinion, let's just figure out y1 first. Seems to be the easiest way to go. So y1 is L tan theta 1. And then we're going to use a small angle approximation. So it's L sine theta 1. Right? But look, sine theta 1 equals 1.22 lambda over the diameter. So we just substitute. So we have 1.22 lambda over the diameter times L. And all right, so that's y1, but then the width equals 2y1. So just 2.44 lambda L over d. And there you go. All right, that's the width. And we'll use that later. All right, we'll use that later. All right, now let me end this chapter with a really cool true story. So I'm just going to read this, and I'll explain it. All right. So remember, in the 1800s, this whole thing was being developed, this whole wave theory of light. But you had Newton who said, no, light's made out of particles. Then you had other people that said, no, light's made out of waves. Okay, so there's a big controversy, right? So let me read this. So this is about two guys, Fresnel and Poisson, French. Okay. In 1819, Fresnel presented to the French Academy of Sciences a wave theory of light that predicted and explained interference and diffraction effects. Almost immediately, Poisson pointed out a counterintuitive argument. Poisson said, to Fresnel, he said, according to your wave theory, if light from a point source were to fall on a solid disk, some of the light would be diffracted around the disk's edges and would constructively interfere at the shadow's center. Now I'm just going to exaggerate. So then Poisson said, anybody with half a brain knows that doesn't happen. Okay, so basically this is what we're saying. So the wave theory of light predicts if light hits this solid disk, well, it will diffract, right? It will diffract around it, and it will form a bright circle right in the middle of the shadow of this thing. So Poisson pointed that out. He said, come on, that's crazy. You know it's crazy. Well, let me keep reading. This prediction seemed very unlikely. However, when the experiment was actually performed by another guy, Arago, the bright spot was actually seen at the center. So, I'm sorry, in McKay 132, I have a demonstration of this. So I use a pinhead. So it's kind of a big, one of these big pinheads that you stick things on to a cork board or something like that. So I have a pinhead, and then I shoot a laser at it, and I use some lenses, but that doesn't matter. And so I'm at one end, I'm at the back of the room, and I do this, And at the front of the room, you know, you see the shadow, but then when you turn the lights down, and then you go up to the shadow, and you see a bright spot right in the middle of the shadow. So come on, does that say that the wave theory of light is correct or what? You know, wave theory of light. All right. So it's kind of funny because, so Poisson, you know, he's the guy that said that, you know, Fresnel is crazy because anybody with half a brain knows that's not going to happen. So Poisson was a pretty famous scientist, but guess what he's known for primarily? For saying that this wouldn't happen when it actually really happened. So he's primarily known for something he did that was wrong. Kind of funny. All right, so my gosh, we did a lot this chapter. So wave optics, the wave theory of light. We use the wave theory of light, and we haven't talked about that yet. We will, don't worry. Understand how the index of refraction affects light waves in medium, right? Light slows down when it goes from air or vacuum to something else like water or glass or something. Path length difference, we did this in 105. Understand the importance of path length difference in determining the kind of interference, constructive or destructive. If the path length difference is a wavelength or 2 or 3 wavelengths, constructive. If it's half wavelength, 3 half wavelengths, destructive. We calculate the positions and angles of bright and dark fringes in double slit. You better know how to do that. Diffraction grading, we talked about diffraction grading. Thin films, woohoo, thin films, right? Diffraction again, and then single slits and circular apertures. Now, you know, usually I give you this review. I have a whole bunch of slides to show you. But, you know, this chapter, just lots of equations, right? So there you go. Sorry. Here's the review of the chapter, just all these equations. Don't memorize them, just know how to use them. Speed of light. Okay, we learned this before, but we're talking about light, so we put C instead of V. Index of refraction. V is always less than C, so this number is always greater than 1. Okay, this is what we learned before. Path length differences. M lambda constructive, m plus a half lambda destructive. Okay, we derived all of these double slit equations, right? And you better know how to do that. Diffraction is proportional to lambda over A. And then we did this wave reflection thing. If you go from small n to large n on a reflection, you get a lambda over 2 flip. Go from large to small, no flip. And we talked about the analogy with a discontinuity in rope. Okay, single slit, all right, single slit diffraction. We get that big central, that bright big central max. This is the equation for destructive, though. Don't forget that, you know. And then this is the width. We'll use that again. And then we did the circular aperture. By the way, look at, this is a wavelength over a width, you know. This is like a wavelength over a width, kind of like, you know. And again, this is incredibly important for astronomy. And that's why they have to spend big bucks to get larger and larger D, so they get smaller and smaller angles so they can separate things that are close. Thank you very much. That's it.